of this whole review sheet deals with counting. And I know you know now what I meant to say in the beginning of the semester, how important it is, how fundamental it is to do probability really well. So of course, the first order of business is understanding fundamental counting principle. And then embedded within all of this is factorials, of course. And you have the counting technique of permutations and combinations. And then I give you an extensive amount of problems for each technique, and then more on counting. So there's more combinations. And this is when you go beyond just finding the combination, you have most likely to find a combination of one thing times a combination of another thing. So this is this section here. And then counting by casework. We have to consider the different cases and complementary counting. So these are the problems that I have for you for today. And then I'll upload the rest either by Thursday or Friday, most likely by tomorrow. And it's gonna the rest of it will be on the stuff that you've learned about probability. So mutually exclusive events, sample space, independent events, inclusion exclusion principle. That's one thing. And then conditional probability is another big one, which is what we did last time. Bayes formula, law of total probability. So those are like the major concepts. So basics of counting, more on counting, all of these different techniques, probability, intro to probability that we've done, and conditional probability. So you'll be tested on those four major concepts. Okay. So as you can tell, there's a lot of problems here. We're not going to be able to cover everything, and that's always nearly impossible to do. Unless you guys have a particular question you want to go over, we can do that. You have a particular question from the homework you want to go over, we can do that as well. So this is very open for you guys to, get the help that you need if you need them. So is there anything on here, for those of you who have it, can see it, that you have a really burning desire to try? You want to go with the fundamental counting principle first, so we can do that. Permutations first, combinations, anything on here? I'm trying. Okay. Is that a good even, Alexandra? You generally, yeah. Oh, okay. Good. So nothing here is compelling for you, I would say. Some of them are not that easy. Let me just say that. Yeah, this one is a good one. This one's a nice one. It appears to be simple, but then when you try it, you're like, wait, what? At first, of course. So anybody have anything pressing that they want to look at? If not, I'll just, start with, I'm not going to start in sequence. I'm going to try to like jump around unless somebody has something that they want to look at. Let's look at number 5 here in permutation. Yeah, so let's look at number 5. And in particular, let's do D. So this is one of those problems, right, where you have a word and you have repetitive letters, and you want to rearrange those letters and find out how many rearrangements are possible. So let's look at the word excellence. I want to know how many ways I can arrange the word excellence to create different letter arrangements. So let's look at that one. So this is 1.2, number 5D. This is number. So here we have the word excellence. There's several letters that are repeated, right? So what are the repeated letters? We have E, right? We have L, and we have C. So how many times is E repeated? 4 times, right? L is repeated twice, and C is also repeated twice. So how many different arrangements? So total number of arrangements. So what's the total number of arrangements? What's the idea again, guys? How do we approach this? Anybody remember how to deal with this? We do have to divide out the copies. So the first idea is we treat all the letters as distinct, right? We treat them as different. So the first E is E1, the next E is E2, E4, E3, and E4, right? So we have 4 E's. And then we do the same thing for C's. We call this is the first C, this is the second C. This is the first L, and this is the second L. So in a sense, we make believe that all these letters are not the same, they're all distinct. So they're distinct objects. So we have how many of those? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 10 letters overall, right? So we have 10 letters. So if I were to arrange 10 objects, 10 letters, 10 of anything, it would be 10 factorial, right? But we have repeated letters. So for every one of these permutations, for every single permutation that we have, arrangement of letters, there's going to be a way to rearrange these E's and it gives results in the same arrangement. Because that's included in this number, I want to divide out that repeated number of arrangements. So I have to divide by 4 factorial for the E, and I have to also divide by the 2 factorial for the L, and then the 2 factorial for the C. And so this will be the number, right? Very good, Christian, that's right. And so then I'm gonna do this by hand, just to make sure you guys see that we can do this by hand. We don't need a calculator for this. We have 4 factorial times 2 times 2, right? Because 2 factorial is 2. You can divide out the 4 factorial, and you can divide out, well, I'm missing a number here. I'm missing a 6. So this is 6 times 5 times 4. And then the 2 can go into the go into the 6, and then this can go into the 4. So what's left is 10 times 9 times 4 times 7 times 3 times 5. And what is this? This is a 90 times 4, which is 360, times 7 times 15. 360 times 7 times 15 is This is 105. Then you have two 3-digit numbers. 360 times 105. 37,800. So there's 37,800 different arrangements. Any questions about this? If it says on the test, it says that they are distinct, then we don't need to divide. Well, yeah. The whole division process, the whole division step, when you divide out, dealing with arrangements, you're essentially saying that we're dividing what's repeated. So if I gave you a word where there's no repeated letter, how many arrangements can I make given those letters? It would be the number of letters factorial, and I wouldn't divide by anything. So a problem like this that you're thinking of would be one of these, where this yeah, so a problem setting that you would be considering is, it's as if I were to say how many ways, right? How many ways or how many arrangements are there for 8 people on a line? So when we say 8 people, right, we are assuming automatically that these 8 people are not the same people. They're distinguishable, quote unquote, distinguishable objects. Because one person is different from the rest, then it's pretty straightforward how many ways I can arrange 8 distinct different things. It would be 8 factorial, and I wouldn't be dividing by anything. That's doesn't really come often. Sharing that question that you're asking, if you have a word with repeated letters, yet you treat them as different. It's not so common to think of that, to come across that problem. But if you do, then you're right. If someone says, hey, I have these letters and I'm treating them as distinct for those that are repeated, then there won't be any division to do. You won't have to divide anything. So it's a lot about the way it's worded, is how the problem is presented, which influences what you have to do. Okay, so when you have repeated things, you divide. If there is no reason to deal with the repeated objects of any sort, then you don't have to divide at all. Okay. All right. So that's this one here. Not too bad, right? We've done this in the beginning a lot. So permutations. What else we have here? Let's see. Oh, I like this one too. So let's look at this one. Combinations. Number 5. So we have what's called a regular octagon, and you guys have heard of octagons, hopefully, most likely, right? It's a polygon with 8 sides and 8 vertices. And the question is, how many triangles can be formed using those vertices of the octagon as vertices for the triangle themselves? So a little bit of geometry here, just to show you guys that mathematics is not so compartmentalized as it may appear to be. There's a lot of overlap with other subjects, fields in mathematics. Yeah, I'll write it again. And again, you guys should be able to see it on CUNY Blackboard. This is on CUNY Blackboard. It's uploaded. So this is 1.3, number 5. So we have a regular octagon. So a regular octagon. Try to draw this thing. So this is 1, 2, 5, 6, 7, 8. Okay. So this is my octagon. Of course, not drawn to scale. Regular means that every angle inside and every edge is the same. So we have 8 sides and then 8 vertices. What I want to do is make a triangle. So for example, one triangle could be selecting one of these vertices. And I made a triangle, right? And I want to find, what I want to find is how many different triangles can I make if I use the vertices of this octagon. So what do you guys think is the correct answer here? How would we find it? So number of triangles that we can make. So Hijab says 8 times 7 times 6. And why do you think it's 8 times 7 times 6? It's a good idea. It's like you're on the right track. But why do you think it's 8 times 7 times 6? Take 8 vertices and then take the remaining 7. Yeah. So that's actually a good approach. So you're saying that you can choose any of the 8 first. Once you make that selection, you have 7 to choose from. And then you can make that selection. So I'll just say I selected this one, then I selected this one. So then I have 6 left to go. And then I selected this one. Does anyone see why 8 times 7 times 6 is a bit too much? But yeah, the order doesn't matter. That's right, Siri. So Hijab, that's a great idea, what you just said, right? But there's a little issue with that, because once you make this, right, you say this is 1. Too much because you're not getting rid of the unused vertices. Well, it's not even about the unused vertices. It's just that the number 8 times 7 times 6, right? It contains this triangle that we formed, right? This is a triangle that we formed. But how did I count this? I counted it this way. I said this vertex, this vertex, this vertex. And then this number 8 times 7 times 6 contains the same triangle more than one time. I could also say I got this vertex, then this vertex, then this vertex. Or I can say I got this vertex, then this vertex, then this vertex. So the 8 times 7, there we go. 8 times 7 times 6 is counting the triangles, but they're counting it a repeated number of times. So Sering is correct with this. This is a very simple answer, but it takes a little bit more interpretation behind it to arrive to that conclusion. To make a triangle, all I need are 3 vertices. Which vertices are they? I can choose this one first, this one, then this one. I can choose this one first, then this one, then this one. I can do this one, then this one, then this one. In the 8 times 7 times 6, the order of the choice of vertices counts. But as you can tell, I can create this triangle without having to worry about the order of the vertices that I select, as long as I select or choose 3 vertices. So the number of triangles that can be formed is simply 8, choose 3. And that's it. So the answer is simple, yet it takes a little bit to think about why that's so. So 8 factorial over 5 factorial times 3 factorial. So you see how this happens here? 8 times 7 times 6 times 5 factorial over 5 factorial times 3 factorial. The 5 factorials cancel. So see, Hijab, your numerator has the numbers 8 times 7 times 6, which is what you expected. But you have to divide out the repeated the repeated ways of getting these vertices. There's 3 factorial, there's 6 ways to select these vertices in order, right? If and it would make a little bit more sense if I were to say use A, B, C, D, E, F, G, H. So in selecting B, D, G, right, I can do this how many ways? I can do B, D, G. I can do B, G, D. I can do D, B, G. I can do D, G, B. I can do G, B, D. I can do G, D, B. Like we've done this already, right? You see how nice this problem is? Yes, I agree as well, Alexandra. Very nice problem because it's I could have just asked the question, oh, how many how many ways can I select 3 letters out of 8 letters? That's the problem that we've done, right? But embedded in this geometric problem is the same problem I just mentioned. The structure behind this question is the same thing. It's just a different perspective. It's a different light. It's more of a geometric problem. But see, that geometric problem is really just a counting problem that we've seen before. So this is really just 56. There's 56 triangles. Okay, so we took out the repeated triangles that are counted within the 8 factorial ways. The 8 times 7 times 6, pardon me, the 8 times 7 times 6 ways. Nice, right? Okay, great. I like this problem too. So we've done a little bit of permutations with repeated letters. We've done a little bit of combinations where the order of the objects doesn't quote unquote matter. So let's see what else we have that might tickle your fancy. So yeah, maybe we can, let's try number 5 for 1.1. I really like this one. It's nice. This is a nice one. One of my favorites here from this review sheet. So this is the problem here we have. Pizzas at Mario's come in 3 different sizes. So you can assume small, medium, large, or individual size, a medium pie and a large pie, right? And you have your choice of different toppings. Oh, actually, yeah, it's the pizza slices. The pizza slices come in 3 different sizes. Or you can talk about the pizza pies, either way. And you have your choice of 9 different toppings, up to 9, including 0. So you can say, you know what, I want just plain pizza. You say, I want pepperoni, or you can say I want anchovies, or you can say I want pizza, pepperoni and mushrooms, so on and so forth, right? And the question is, how many different orders of pizzas are there at Mario's? Who orders pizza without toppings? Hey, I know people that they just want plain, and that's fine. I like plain too. I like my pepperoni as well. So think about this. It might be a little too early for pizza right now, but the pineapple, okay. I already know about that whole that whole controversial topic. Pineapple, no pineapple. Um, so think about this, guys. You have three different sizes for the pizza pies, and you have nine toppings to choose from. You can choose none of the toppings. You can choose one of the toppings. You can choose two of the toppings. You can choose three all the way to nine. So the question is, how many different choices are there? Yeah, let's talk about that. Let's talk about probability pineapple pizza. This is 1.1, number 5. So we have different pizzas. I would just call them small, right? Medium, and the large. Oh, no fruits for you, Oliver. No strawberries on pizza. And then you have 9 toppings. Hijab, it doesn't matter if it's slices or it doesn't matter how you interpret the slices or pies. You just have pizza. So you can have it in a pie form, you can have it in a slice form, but just choose one, right? So if you're dealing with pies, then just deal with pies. If you're dealing with slices, just deal with slices. We're not saying that these are two different things. So either you go to Mario's and say, hey, I just want all pies. You know what? Let's just stick with pies. I don't want to confuse anybody. So make believe they're just pies, okay? So 9 toppings plus no toppings is a total of 10 choices. You can think of them as 10 different, yeah. If you're looking at it from that perspective, you have 9 toppings plus the idea of having no toppings. So you have, in a sense, 10 different variations. That's one way you can think about this. But you also have to consider that you can select uh, more than one topping at the same time. So you can select 3 toppings. I want 3 of those toppings to be on my pizza pie. So this question can be solved more than one way. It depends on how you view it. We can do cases, hijab. Yes, we can. And this problem is under the section of fundamental counting principle, which means is you can solve this without cases. That's the beauty behind this problem. You can solve it without cases, but of course you can use case work to solve this. So it depends on how you view it. So when you say cases, hijab, what do you mean? How did you choose choice of choosing one topping? Okay, so we can do by number of toppings, right? If that's what you want to do, that's okay. So uh, applied casework on number of toppings. So the first case, right? Case 1 is what? 0 toppings. I just have plain. And how many ways is that? If I have no toppings on my pizzas, how many different pizzas can I have? I have three, right? Three choices. Why are there three choices? Because I have three different sizes for pies. I can either have a small plain pie, I can have a medium plain pie, or I can have a large plain pie. And that's it. That's all the different ways. Good? Case two, I can have one topping. How many ways can I have one topping pizza given the number of pies and the 9 toppings? Three times 9, very good. Thank you. That's right. I have 3 choices for the number of pizzas, for the types of pizza sizes, and then I have 9 choices for the toppings, just selecting one. So that's going to be a total of 27. Awesome. Next. How about case 3? 2 toppings. Now this is when it gets interesting. I want 2 toppings. So how do I get the number of pizzas with different sizes that have 2 toppings on them? Christian says 3 times 9 times 8. So Christian, why do you say 9 times 8 divided by 2? Oh, where did divided by 2 come from? Oh, and then you multiply by 2? Saring, is that what you do? So what do we do? We multiply 3. That's a fact because the 3 is going to be embedded in all of these cases, right? You have 3 different sizes, so 3 will always be there. Now think about the next thing. I want 2 toppings. Does it matter that I choose pepperoni first and then mushrooms? Compare with mushrooms first and then pepperoni? Does that matter? It doesn't. I'm still going to have a pepperoni mushroom pie. So when you just do 3 times 9 times 8, you're essentially saying the order of the toppings for the 9 and 8, it matters. You're saying that, hey, if I get pepperoni and then mushroom, it's different from mushroom and then pepperoni. And then Daisy says, let's divide that by 2, which I would agree with. So this is actually 3 times 9 times 8 divided by 2, which is 3 times 72 divided by 2, 3 times 36. And this becomes 108. There's 108 ways. That's crazy, right? To have 2 pies, one pie with different sizes, utilizing 2 toppings. Is there another way I could have thought about this? So this is one way I thought about, right? I found 9 toppings, then I choose another 8 toppings. Then I realized, hey, the order doesn't matter. And then I divided that by 2. And then Christian, very good. You could have also thought of it this way. Alternatively, you could have said 3 is choices, or you could have thought of it as 3 choose 1. I have 3 choices, choose one of them for the size of the pie, and then multiply that by 9, choose 2. 9 choose 2 is exactly 9 times 8 divided by 2, because if you do the apply the formula to this, right, you get 7 factorial times 2 factorial. And then the 9 times 8 times 7 factorial, the 7 factorial cancels. And you're left with 9 times 8 divided by 2. Do you see that? We get to the same, we arrive at the same conclusion. We arrive at the same conclusion that 3 times 36 is 108. That's another way to think about it. And I think this way might be a little bit easier now to apply for the future cases, right? So we can already even just we don't even have to go through every single case anymore because we kind of see the pattern. If we have 3 toppings, then what happens? Then I do 3 multiplied by 9, choose 3. 9 choose 3 becomes what? This is 3 multiplied by 9 factorial over 6 factorial times 3 factorial. This becomes 3 times 9 times 8 times 7, right? Over 3 times 2 times 1. The 3 goes into the 9 3 times. The 2 goes into the 8 4 times. So I get 3 times 3 times 4 times 7. This is 9 times 28. And 9 times 28, we get 2, 7, you get 252. So does everybody see what's going to happen next? There we go, Hijab. That's right. Cut straight to the chase. Do you see that? You see how beautiful counting is? It's a structure behind this. It appears that we're talking about pizza, talking about pineapple pizza, but there's a structure. There's a combinatorial underlying structure behind all of this. It's very nice. So that's basically what you're trying to find out. You're trying to find out, hey, what is the organization of this the counting that I need to do? It's really an organization of of objects. So we know if we do 4 toppings, we do 3 times 9 times choose 4. If there's 5 toppings, 3 times 9 choose 5, and so on. If there's 9 toppings, 3 times 9 choose 9, right? So the total number of different pizzas is equal to 3 multiplied by 9 choose 0 plus 9 choose 1 plus 9 choose 2 plus ... 9 choose 8 plus 9 choose 9. And then we know what this is, right? 3. I can also write this. I like using shorthand the summation notation. I can write this as 9 choose I as I goes from 0 through n through 9. So this is 1 plus, what was it? 1 plus 36. No, sorry, 1 plus 9 plus 36 ... plus 9 plus 1. So can anyone tell me what this number is? Anybody have a calculator on? Can you guys compute? What would be the sum of all of this? I think, hold on, I think you can actually, yeah, so you guys need help with this. You can actually put this in your calculators to help you out. So let me just share my screen here. So you go to second and go to a window. And what's nice is you have a summation notation here. So you can actually like write it out. You got 512. So you got 512 for what? For the sum, right? Of the binomial coefficients, right? And then you have to multiply that by 3 because you have, yeah, 1536 should be, that's right. 1536 should be the correct answer. So let me just show that to you guys here. Uh, let's see. Oh, Wolfram Alpha, yeah. Wolfram is incredible for mathematical computation. It's one of the best mathematical engines that have been created. Yeah, Wolfram Alpha. And yeah, Wolfram Alpha is really good. Let me see. I think we can use this. I go from 0 to n, and then this goes to 9. And I use math probability here. The first number would be an n, 9, and the next number would be the n. Enter. 512. You see that? So what I counted here is exactly the sum of the binomial coefficients: 9 choose 0, 9 choose 1, plus 9 choose 1, plus 9 choose 2, plus 9 choose 3, all the way to 9 choose 9, 512, and then you multiply that by 3, and you get 1536. So everybody okay with that number, right? 1536. So that's the number. Now my question to you is there a better way? A more efficient way? Is there a way that I can do this without cases? Is there a way I can do this without combinations? That's really my question. So this is 3 times 512, which is 1536. There's 1536. There's 1,536 different pizzas orders that I can make under this circumstances. So I'm gonna say this. This is solution number 1. This whole thing is solution number 1. And of course, right? Wait, have you guys, for those of you who have done computer science or are doing computer science, have you guys done the 8 queens problem when you're doing C++? I feel like everyone has done that, right? Yeah. They love that problem. So it's one of those things, right? You solve the same problem like 8 different ways, and every single time it's like better, more efficient, less time consuming, right? There's like they would say the dumb way or the brute force way, and then there's like the really slick way with recursion, and how to write it in the brute force method. It's like all these nested for loops, but then in recursion it's like one single line. So it's kind of like that. Like this solution here is systematic. It gives you the right answer, and it's nice to look at it this way as well. But there's actually a way to look at this that summarizes all that we've done without actually dealing with the cases, and it does it almost in one line. So again, this problem was not in the combination section, which is, it's okay though if you solve it with using combinations, and if this way is what you see and how you see it, that's fine. But I just want to show you that there's another way of looking at this. And I like this way because it makes you see that, oh wow, there's actually much more efficient ways of doing this. And then it makes even the problem, the solution that we just have, it makes that even make more sense. So what I'm going to do is I'm going to consider this as slots. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. We have 10. Why do we care about the number of slots? Because what I'm going to say is, hey, I'm going to say this. This is the size of the pie. This is the first topping. Or if I want, I'm just going to say this is pepperoni. Uh-oh, Pascal's triangle. Yeah. The moment you talk about combinations, Pascal appears. What's the next topping? Mushrooms, right? What's the next one? What do you guys like on pizza? Sausage, okay. Like sausage. What else? Broccoli. Oh, pineapple, of course. Whenever uproar with the pineapple. Bake, you had onions. Okay, you got onions. You have chicken. Bacon. Okay. Bacon. Let's do spinach, okay, for the healthy green people. And basil. Basil's good. You had that margarita pizza, it's good. But I'll just put garlic. You can choose any arrangement that you like. So look at this now. This is where it gets really nice. So how many ways can I select? How many pies do I have to choose from? 3. And now the question is, how many ways can pepperoni exist? Right, Ethan, that's right. That's really nice about this because either pepperoni can be on the pizza or it can't be on the pizza. So I have so pepperoni has 2 states. It could be on or off, 0 or 1. Here we go with the binary stuff. So there's 2 choices. But wait a minute. Mushrooms has the same situation as the pepperoni, right? It also has 2 choices. And it also has 2 choices. So on and so forth. So this number is really 3 times 2 to the 9th. And guess what 2 to the 9th is? It's 512, which equals 1536. When you look at it from this way, you're like, what? Right? You're like, wait, I could have done this the whole time. But do you see, that's the beauty behind this. It's how you view it. So if you use that casework mentality, then you're gonna have these different combinations to compute. You're gonna have to sum it up, find times 3, blah, blah, blah. That's fine. But then if you view it from the fact that, hey, can pepperoni be on or off? Can mushroom be on or off? Can sausage be on or off? Pineapple on or off? Multiply that by the fundamental counting principle because one decision, right, affects the choices of the other ones when you want to count them out. So that's why you multiply. And if you were a little bit more perceptive, you should have seen this already. Someone mentioned Pascal's triangle. I'm pretty sure I mentioned that if you look at the Pascal's triangle is related to the coefficients, right? The binomial coefficients, which is the 9 choose 0, 9 choose 1, 9 choose 2. This is going to be, these numbers that appear are going to be on the 10th row of the Pascal's triangle. And if you add that row, each of those rows, there are powers of 2s. So someone could have been like, hey, wait, this is that row on the Pascal's triangle. And if you add these numbers, you do get 2 to the 9th. That is 2 to the 9th. But anyways, very nice. I really like this problem. It's a very nice problem because there's 2 ways to look at it. And there's one way that simplifies the problem much easier, but it's harder to see it, right? It's harder to see this underlying structure, which is a different way of looking at it. And embedded in this product are all these cases, nine toppings, 8 toppings, all the way to no toppings. Cool, right? I like this one. It's my favorite one on this review sheet. Okay, great. Great. Any questions about this? Any questions about the different solutions? Um, so factorial form would be fine. Like you don't have to do this every time. Um, if you leave it like this in this form, that's okay. I mean, solution number one. What do you mean? Like you want to just leave it like this, or are you talking about like this? Um, I wouldn't just leave it this way. I wouldn't. I wouldn't accept this just to be. It does tell me that you do know what the answer would be, but I think getting up to this should be fine. Like that's not that much, right? It's not. It's not. I'm asking like that much from you. Um, but yeah, there might be some numbers that are too big, so factorial form would be perfectly fine. Do we get to use a calculator? Yes, you do. Yes, I am allowing you to use a calculator. Okay. So any questions about this further? The same one. Yeah, the same one. Sharing the same calculator that we use. TI-84. Perfectly, perfectly fine. Perfectly standard for exam like this. Okay. So we dealt with 3 problems so far. I guess we should go look at the other page just to make sure we're okay with all of the stuff here. So this gets a little bit more complex with the counting. Um, so the first part, of course, is much more of the basic introductory techniques of counting that you guys now, I'm pretty sure, are really comfortable with. So let's look at this. Which one seems interesting? So let's see. We can do number 4 for combinations. Whoops. We have a standard deck of cards, and this is pretty standard. I'm pretty sure, hopefully, everyone knows what a standard deck of cards is. It's 52 cards. You have 4 suits, 13 cards for each suit. And then it says how many 7-card hands will consist of 3 jacks and 2 aces. And this is a problem you've definitely have seen in your homework problems. So this is 2.1, number 4. So you have a 52 card standard deck. You have a 7-card hand. So your hand has 7 cards. And in this hand, I want to have 3 jacks, right? Three jacks and 2 aces. How many different 7-card hands are there? So how do we treat this? How do we view this? How do we approach this? Anybody have an idea? So the seven card hand, the only requirement for the seven card hand is having three jacks and two aces. So that consists of only how many cards? Five. So the other two cards that I have in this seven card hand could be anything other than jack or ace. Right? So that means, let me just write that. So the two other cards could be anything that are not, that are neither a jack nor an ace. Right. So how many ways is that? Well, I have three jacks to choose from. How many do I have to select? I got four, choose three. And then I have four aces and only want two of them. So that's four, choose two ways. It's gonna be six different ways, right? So this is four, this is six. But then the rest of the cards, how many cards do I have left that I don't include? I don't include if I have 52 cards and a total of four jacks and four aces, the rest of the hand cannot be a jack or an ace again because I already got them already. I already this number here already includes this requirement, having three jacks and two aces. I can't have more than I can't have another jack and I can't have another ace. So then I need to subtract 52 minus 8, which is 44. I have 44 cards to choose for the last two. So that would be 44, choose two. And 44, choose two, I can also compute it as 44 factorial over 42 factorial times 2 factorial, which is 44 times 43 over 2, because the 42 factorials cancel. This becomes 22 times 43. And you can multiply that out. You can put that in your calculator. 22 times 43 is 946. So there's 946 ways. And then when you multiply things out, 4 times 6 times 946, I have 22,704 seven card hands. Those are right hands. Nice, clear, not bad, right? So this is when you had to deal with combinations, but now you're using combinations in by applying the fundamental counting principle with it. So you have very numerous combinations that you deal with and multiply and compute the product. Okay, any questions about this problem? Clear? Clear as crystal. Okay, so we have that. We got 10 minutes left, 9 minutes. Let's do something by casework. So I guess I didn't put that one. Okay, so let's look at number three. Oh, number five in complementary content. Okay, that's fine. Let's do that. Okay, so a person has 8 friends, of whom 5 will be invited to a party. How many choices are there if 2 of the friends are feuding and will not attend together? Uh, so how do we approach this problem? So this is number 5. This is a 2.3. 2.3. 2.3, number 5. And again, some of these problems can be solved more than one way. So maybe you don't see it as a complementary counting problem. Maybe you just see it as a straight up casework problem. Um, yeah, so they're feuding, right? What does that imply for us? What do we infer from this? If they're feuding, then you can't have them in the same, you can't invite them to the party at the same time. So you see how you can deal with casework here? You can say, hey, what if one of the friends is invited, the other one is excluded? What if the other one that was excluded is invited and the other one that was invited is excluded? You count that. So you can consider this problem from a perspective of casework. But there's also a complementary counting technique or viewpoint that you can approach this problem with. So what's the opposite of them feuding? What's the complement? That they get along. Exactly. So then how many ways are there for them to get along? That might be a little bit easier to deal with. And then subtract that from the total number of ways of um, the total number of ways of selecting 5 people. So what's the total number? That's always the start, right? What's the total number of ways to invite 5 people among 8? Basically, how many groups of 5 people can I make out of 8? That should be straightforward. It should be what? 8 choose 5, right? Again, we use these two notations as the same, but this notation is much more common. 8 choose 5 for binomial coefficients. And so then 8 choose 5 becomes what? 8 times 7 times 6 over 3 times 2 times 1, which is 56. So there's 56 different ways. Now, how many ways are there? Number of ways to invite the 5 people where the two feuding people friends have reconciled. And are together. So how many ways can I do that now? What if the feuding friends are in good terms again, and you want them to be invited in this group of 5 people? How many ways is that? Isn't what the same? No, I'm saying I want them to be included in the 5. So if they're included within the 5 friends, then there's choose two ways of selecting those 2 friends, and then multiplied by, well, how many friends do I have left? If I chose 2 already out of the 8, then there's 6 ways. There's 6 choices to choose from, and there's 3 people to choose from from that group. Do you see that? So it's not the same. So I'm saying, yeah, so maybe I should specify this. There's a number of ways to invite 5 people where the 2 shooting friends are included within the 5. Yeah, we're including them. So we're including them within the 5. So they're both included within the 5. Within the 5 people. Again, we're doing complementary counting, right? So they want to know how many ways can you create a group of 5 people where there's 2 people that can't be in the same group. So then we're saying, okay, that's fine. We can look at it that way. Or we can say, hey, what if they were invited and included? How many ways is that? And so then we find the total number of ways of just forget about everyone's great, right? So you can have them together. You can't have them together. It doesn't matter. There's 56 different ways. And then what if they are together and they're all good? So once I choose those 2 people, I have 6 to choose from, and I'm only selecting 3 of them to complete the 5. So this would be what? This would be 6 factorial, because 2 choose 2 is 1. 6 factorial over 3 factorial times 3 factorial, which is 6 times 5 times 4 over 3 times 2 times 1. The 3 and the 2 cancel to 6. So I'm left with 20. There's 20 ways of having the 2 feuding friends being together. Now, one more scenario we have to consider, right? Because we want to figure out, again, what do we want to figure out? How many ways are there if the two choices are the 2 friends are feuding? So is this enough? If I were to do this, if I were to do 56 minus 20, I get 36. So is that enough? The number of ways that I can have a group of 5 people where 2 of the people can't be together, right? They can't be together. So I found the ways that they can be together. So definitely they can be together 20 different ways. If I subtract the 56 total ways with the 20, I'm left with 36. So what does this 36 contain? What does this 36 contain? It contains the ways that the feuding friend, that the friends are not. Yeah, they both don't attend, or one of them attends and the other one doesn't, or the other one attends and the other one doesn't. So this is enough. Just to corroborate this, right? Just to make sure this is the correct number, you can think of it from the casework perspective without the complementary counting. You can think of, what if one person is in it and the other one doesn't? And then because of the symmetry, if you include the other perspective, the other scenario where the excluded friend is included and the other person is excluded, it's that same number. And then you have to also consider the fact that none of them are, because that's fine, even if they were feuding or not feuding, right? Isn't that part of the way of selecting 5 people? Those 2 friends don't have to be included in the number that I'm looking for. I'm just looking for the total number of ways of having people where 2 of them can't be on the same one. But actually, those 2 people don't actually have to be invited. So that would be 6 choose 5, which would be 6 ways. So this number is 36 is the correct answer for that. Okay, does that make sense? So I'll stop right here. Okay, guys.